Hello, everybody, and welcome to your fourth lecture for historical geology. This is Dr. Hurt, and we're going to be talking today about minerals. Or I guess I'm going to be talking. I can't really talk to you over online, unfortunately, so it's just going to be a one-sided discussion, I guess. But anyway, just going to get right into this material. So first slide is kind of cool. This is maybe some of you have seen this before. I know sometimes they put this on like History Channel or National Geographic Channel or stuff like this. But this is a real famous cave in Chihuahua, Mexico, that has these huge crystals. And it's kind of cool because, you know, if you didn't see this guy, you might just think that, oh, this is like a close-up of a geode or something like that. But it's not. So the crystals are really that big. And those are made of a mineral. Actually, all crystals are not necessarily minerals, but so this thing, not all crystals are minerals, but all minerals can crystallize. So I guess that's the way I should state it. But these are gypsum crystals. Gypsum. Some of you maybe like know the stuff you can get at like gift shops called like selenite, things like that. That's gypsum. Same thing. So anyway, hot water had filled up with that cave and precipitated out those big crystals. Just very similarly, if you've ever like left some maybe some of you've like left salt water or even just regular tap water out and let it dry, you know, it forms some mineral deposits. And now that's like hard water, right? Sometimes you get mineral deposits around your sink or around in your pipes or whatever. That's all mineral deposits actually. So minerals are so valuable to us in earth sciences and historical geology because, my gosh, they provide a record of so much information, very valuable record of so much information. They're just packed and loaded with lots of information for us that we can look at and figure out like what the heck has happened in Earth's history. So all rocks are composed of minerals, okay? All rocks are composed of minerals. So minerals are the components of rocks. So rocks are usually just conglomerates of different kinds of minerals. Sometimes it's made of one mineral, but it's always made up of minerals, okay? And they can tell us so many things. They can tell us what the rock is made of. They tell us how the rock formed. They can tell us the pressure and temperature that prevails at the time it was formed. It can tell us how the rocks have been modified or changed by maybe, let's say, weathering or maybe from biologic activity. All these things. It's just overwhelming how much. I just give a few examples here, but it's overwhelming how much information is contained in these things, right? So, for example, if you get a beautiful peridotite rock from the mantle, these contain the minerals olivine and pyroxene. And we can actually figure out, looking at those minerals, exactly what pressure and temperature that rock formed at. Okay, so we know exactly, like have you ever thought, like, how do we know what the temperature of the mantle is or the pressure of the mantle is? Well, we know it from the rocks that come up from the mantle, okay? Related to that, in places where we find coesite is a mineral that forms at very, 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 very high pressures. And it only forms on Earth's surface when there's a meteor impact. So if we want to investigate evidence for a meteor impact, and have there been a few meteor impacts in Earth's history? You bet so, right? I'm sure that a lot of you famously know that the dinosaurs, a lot of them died off from meteorite impact, right? And we know that from the kinds of minerals that we can find around meteor craters, right? Calcite is a very common mineral. And it's actually a mineral that is precipitated and created by a lot of different marine organisms, right? So the White Cliffs of Dover in England, if you've ever seen these before, I doubt not many students have seen these in person because, right, so all the way over in the UK. But these were completely created by the plankton that lived millions of years ago. And because the plankton created the calcite, it tells us a lot about what that plankton was like and what the chemistry of the oceans were like at the time. So, man, it's hard to I could go on and on about what we can learn from minerals. So it's extremely important. And if we're going to understand historical geology, you have to pay attention to this lecture because we're going to focus so much on minerals in this class because that's how we know about Earth's history. Okay, so first we got to start off this question like, what the heck is a mineral, right? So there are five kind of defining points that make a mineral. So they're kind of like five things that have to be true in order to be a mineral. So Uh, the first thing is that minerals have to be naturally occurring, so not made in a factory. So these synthetic blue sapphires are not minerals because they were made in a factory. This lovely little diamond from Murfreesboro, Arkansas, it's one of the only places in the contiguous 48 states that you can actually find diamonds naturally. Um, that's a mineral because it's made naturally. Okay, minerals have to be formed by a geologic process. Okay, we're going to go over the different geologic processes that create minerals. So it can't be created by a biologic process. It has to be some kind of geologic process. Okay, so for example, solidification from a magma is one way that a lot of minerals form. So this beautiful olivine crystal here, formed by what? From solidification of a magma. Okay, so the magma cooled, crystallized, and gave us this little olivine crystal. That's a mineral. Another way is from precipitation. These halite crystals that formed in Devil's Golf Course in, what is that called? Death Valley National Monument in California. These are minerals. They didn't form from a magma. They formed from a kind of saturated, briny liquid, water, that evaporated. You know, it's very evaporative conditions in the Death Valley, right? So it evaporated and it left behind the mineral contents. Okay, so they precipitated from a liquid. There's also other things, growth by pressure, and I'll talk about those in just a minute. So here's some beautiful tufa towers. These are made of calcium carbonate mineral called calcite. They've precipitated out of a lake water from hydrothermal activity. So you have these hot water, what do you call them? Hot springs that are just loaded with mineral content. And as they come to the surface, they precipitate out all of that calcite, and you get these towers of calcite that are forming in places where you get hydrothermal activity. So you'll find these all over the place. Anywhere you get hot springs, actually, you get some mineral deposits like this. Okay. So kind of taking a little tangent, we're going to go over the 5 criteria that need to be fulfilled in order to be a mineral. Okay, the 5 things that make a mineral. But kind of taking a little tangent, I want to go into the different processes because there's also 5 processes that can create minerals. Okay, so let's talk about each of these. Number 1 is crystallization from a melt or a magma, a lava. Okay, that's one way. It's a very common way that you create minerals. Another way I already mentioned is evaporation from a liquid. Okay, so like water saturated with salt, saturated with calcium carbonate, saturated with iron, whatever it is. The water evaporates and it leaves behind its mineral contents. Because I'm sure you know that water, it's usually, whether it's your tap water or water, in a stream or in a river or in the ocean, it's not pure water, right? There's other stuff that's dissolved in it, okay? And that stuff's going to be left behind when evaporation occurs. Something you might not think about too much is freezing of a gas. So, for example, places where there's volcanic activity can leave behind a lot of gases, and those gases that are emitted can freeze and form minerals. So, for example, you can see all the yellow sulfur that's being emitted by the sulfur gas being emitted by the volcano. Okay, so another one is growth at high pressure. Now, this is kind of a strange one, but I want you to kind of use your imagination. I give you an example here of a rock called eclogite. Some people call it Christmas rock because it's red and green. Okay, it kind of looks like Christmas colors. I want to give you a different example, though. Perhaps you know this, perhaps you don't, but you can take anything that contains a lot of carbon, and you can put it under sufficient pressure that it will form a diamond. Okay, because a diamond, you might know this, you might not, but a diamond is pure carbon. Okay, it's absolutely pure elemental carbon. It's just the element carbon that's been crystallized. Okay, so you could take, for example, a piece of coal or a piece of charcoal or even peanut butter, if you can believe that, has a lot of carbon in it, and you can compress it and put it at high enough pressures, it will form a diamond. So that's growth of a mineral at high pressure. So for example, is peanut butter a mineral? I hope you're thinking no, right? Hopefully you know peanut butter is not a mineral. But if you compress it and you put it at high pressure, it'll form a diamond. Is a diamond a mineral? Sure is. Okay, so you made a mineral just by pressurization. Now, another thing that's very, very important in our historical geology class is this process of mineralization, aka sometimes this is called biomineralization. But mineralization is when you have non-mineral material, for example, bone or skin tissue or any kind of like living tissues or previously living tissues are not minerals. However, after spending some time underground, there's mineral rich waters perhaps flowing through. Atom by atom, the tissue will be replaced with mineral content, and that's called mineralization. So when you see a skeleton of a dinosaur in the museum, you're not looking at the actual bones of that animal. You're looking at rocks and minerals that have replaced the bone. Okay, that's a very important point. Okay, so I want you all to understand that and know that for historical geology. When you look at a fossil, you're not looking at the actual bone tissue or the shell tissue or whatever it is. Okay, it is now solid mineral, solid rock that's been replaced over the ages. Okay, atom by atom, minerals come and they replace that material, the original material. Okay, so moving on to what is a mineral or what are minerals. Minerals have to be solid. Okay, so this glacial ice, for instance, is a mineral, but the water it comes from, freezes from, is not. Okay. Minerals have to have a crystalline structure. This is one of the most difficult concepts for students to understand. So let me kind of spend a little bit of time explaining this. So, in a crystal, there is an orderly arrangement of the atoms. Remember how we talked about we live in a cosmos where there's order. I don't think that's clearer anywhere else than in a mineral. Okay, minerals, every atom has a place, and there's a place for every atom. Okay, minerals are highly, highly ordered, and that's why minerals. How a lot of people think, minerals have like mystical qualities, metaphysical qualities. It can heal you or whatever. I don't know if that's true or not. I don't do that stuff, but I know some people believe that, and I think a reason that a lot of people do believe it is because minerals do have a lot of very weird properties. If we were in a face-to-face class, I would bring my set of weird, far-out minerals, and I would show you some of these things. But I think that's kind of like why people have this intuition that there's kind of something magical about minerals or something. I don't really think that, but hey, who knows? Maybe there is something like that about minerals. I don't know. But anyway, minerals have this very highly ordered crystalline structure. So you'll notice that this is a diagram of rock salt, halite. Okay, halite is the mineral name of rock salt. Okay, and you'll notice that it's sodium chloride, and every sodium atom is ordered with every chlorine atom. So that's not all jumbled. Like, that's not a big random jumble, right? You see it goes sodium, chlorine, sodium, chlorine, sodium, chlorine, sodium, right? Et cetera, et cetera, et cetera. So you see the pattern. Okay, there's a lot of patterns to things. This is what for example, a mineral arrangement looks like, and you see the pattern, right? Okay, so there's a question like on the back, I think, of your sheet, and it shows you different like atomic arrangements. And the one that is a mineral is the one that's highly ordered, and the one that is not a mineral is more disordered. Okay, so minerals have a definable chemical composition. That's another aspect of minerals. So, for example, galena, right, is a mineral. It contains lead sulfide. Okay, halite is a mineral. It's rock salt. Sodium chloride. Quartz is a mineral. Silicon oxide, right? So this is the thing. If I asked you what is the chemical composition of quartz, you could say it's SiO2. Okay, one silicon atom, two oxygen atoms. But not all materials are like that. For example, if I asked you, what's the chemical composition of wood? Well, I mean, it just varies. Like there's a lot of variation, right? You could have some has more carbon, some has more hydrogen, some has more or less oxygen, right? So it changes. But that's not true with minerals. Minerals always have basically the same composition. Sometimes there's small impurities, but it's always the same, okay? Diamond, graphite, right, both have a composition of C, carbon, okay? Orthoclase, a very common mineral, has this chemical composition of potassium, aluminum, 3 silicon atoms with 8 oxygen atoms, okay? So anyway, you have to be able to write a chemical formula that defines a mineral. So every mineral has a chemical formula, okay? They all have a chemical formula. Now, keep in mind that you can have the same chemical formula in 2 different minerals. Okay, so carbon is the chemical formula of diamond. Carbon is the chemical formula of graphite. Graphite and diamond are not the same mineral. They're very different. The only difference, compositionally they're the same, but the way the carbon atoms are arranged is totally different. And it ends up with very different physical properties. Okay, so moving on here. What do you think? Which is a mineral and which is not? You have glass here, and you have some salt. So the glass is not a mineral. It's not a mineral because glass has no crystalline structure, and it's man-made. Salt, however, is a mineral, okay, because salt is naturally formed by a natural evaporation process of the earth. It's not man-made, and it is got a crystalline structure. So what do you think of these things? Water. Is water a mineral? No, it's not a mineral because it's liquid. What about grow your own rock candy? It looks like a mineral, doesn't it? It's got the crystals, right? But it's not a mineral because it's not naturally made, right? It's man-made. Your teeth. What about your teeth? Are those minerals? Well, those are not minerals because they are created by a biological process, not a geologic process, okay? So we don't consider those minerals. Same thing with this amber here. This amber is, a lot of people might think of this as a rock, but it's not a rock. It's actually just, you might know, preserved tree sap. It's not crystalline. It doesn't have a crystalline structure. And it's also kind of more of a biologic product rather than geologic. But mostly it doesn't have that crystalline structure. Okay, so none of these things are minerals. Just wanted to go kind of very, very quickly over some properties of minerals, important physical properties of minerals. So obviously one of them is color, right? You can have the same mineral, but they can be all different colors. Quartz is a great example. This is all quartz, okay? Milky quartz, clear quartz, rose quartz, amethyst, citrin, smoky quartz, so quartz can be any color under the rainbow. And it arises from impurities or crystal defects. You can get these different colors, okay? But minerals can be a lot of different colors, right? Some of them are very characteristic and can be helpful, but sometimes it's tricky, okay? One thing that's kind of more reliable indicator of what a mineral is its streak color. So the streak is when you pulverize some of the mineral on a porcelain plate like this. It's basically just the color of the ground mineral, like when you grind it up. Some things can be different colors. For example, hematite can be red, it can be black, but it always has this kind of reddish brown streak. So that's really useful indicator of what the mineral is. There's pyrite, which is fool's gold, and it leaves that black streak even though it's gold in color. Okay. Luster is how light reflects off the surface of the mineral. So some have kind of a metallic appearance, some kind of appear silky, some can appear waxy, some can appear greasy, maybe vitreous like glass. Right, here's like minerals with like a metallic luster. Okay, so just kind of giving you an idea of how that, they appear shiny, right? So I'm just trying to give you an idea how these things look. Hardness is very important. This is one of the things I wanted you to be aware of. So different rocks have different levels of hardness. Hardness is how easy it is to scratch the mineral. Okay, so the softest mineral is something called talc. We actually grind talc up and we make something called talcum powder. Have you ever heard of talcum powder? We use that for baby powder. It's so soft, we actually put it on your baby's bottom to dry the baby out. Although, they stopped using it actually because it might interest you to know that talc is kind of similar in its mineral structure to asbestos, which is a very harmful mineral for your lungs. So they've actually kind of stopped using talc so much, even though it is very good at drying your baby's bottom, but it's not necessarily good for your lungs and good for your baby's lungs. Diamond is the hardest mineral. You might know that. Okay, diamond is so hard that they actually take micro diamonds, little micro crystals of diamonds, and put them on saws to be able to cut through rock. Okay, so you just want to kind of know things like talc and graphite are very soft. Gypsum. Okay, gypsum is a very common rock. We're going to learn more about gypsum because it's a common rock that is deposited on Earth's surface through like evaporation. So in places where there's been lagoons, you get gypsum being deposited. Places where there's some kind of like desert lakes will leave behind gypsum. Okay, so it's a common rock. We'll talk about it in this class. So gypsum is very soft. Calcite is so important. Oh my gosh, do we talk about calcite in this class? I mean, it is everywhere, and it makes up a lot of like clam shells, a lot of marine organism shells. They make their things out of calcite. Very, 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 very important mineral. So, oh my gosh, please love calcite, know everything about calcite because it's just one of the most important minerals that's going to be in this class. Okay, calcite is only a number 3 on the what's called the Mohs scale, hardness scale. Okay, so it's pretty low, pretty soft material, and along with this, the softer things are, the softer the minerals are. I want you to think about this. The more easily they're going to weather. Okay, so the more easily they're going to be broken down and weathered and destroyed over the process of erosion. Okay, so these things are going to be eroded easily. Fluorite's number 4, apatite's number 5. You don't need to know those ones too much because they're not very important. Orthoclase is a type of feldspar. Okay, we're going to talk a lot about feldspars in this class. So feldspar, you're gonna learn to know and love it. Feldspar is a hard mineral. Okay, so you can see it's number 6 here. So it's getting pretty hard now. Okay, glass, by the way, glass is about a 5 on this scale. Also, steel is around a 5 as well. So we can put steel and glass right in here. So feldspar is harder than steel and glass. You can scratch steel and scratch glass with feldspar. So orthoclase here is a type of feldspar. We're going to talk about the different kinds of feldspars as we get deeper into the class, but it's a very important mineral. You want to know that one. Quartz. Quartz is also a very important mineral. It's number 7 here. Topaz and corundum, you don't need to know about those so much because they are kind of relatively rare precious stones. Topaz is a precious stone. Corundum is a precious stone. You ever heard of rubies? What about sapphires? Okay, that's all corundum. Okay. Diamond is, of course, the hardest mineral, number 10. Okay. So as you move up this line, by the way, things get harder and harder to erode. They get harder and harder and harder to erode. Okay, so that's kind of why I wanted to talk about this in detail here about hardness, because we talk a lot about erosion and weathering in this class. Whoops, going back. Okay, specific gravity is the density of the mineral. Okay, some things are more dense, some things are less dense. The density of most rocks you're going to see is, remember we talked about density being very important when we talked about Earth structure, right? So you'll find that the density of most rocks is somewhere between like 2.3 to 3.3 grams per cubic centimeter. Okay, so 2.3 to 3.3 is average. So most crustal rocks are going to be like that. Okay, mantle. So most mantle rocks are going to be like maybe 3.5 grams per cc. And then, of course, the core is very dense. The core, you're talking more like 10 to 11 grams per cc. Okay. So just something to keep in mind. Crystal habit, you don't need to know too much about. It's just kind of the form of the crystals that prevail. Different minerals have different forms of their crystal, different shapes of their crystals. Sheet-like, needle-like, cubic, things like that. Right. This very characteristic shape of the mineral beryl. Beryl, by the way, is aquamarine if it's kind of bluish greenish, or it's emerald if it's green. Okay. Crystal habit, you don't need to know too much about this stuff. This I want you to know about. Okay, certain minerals just have special properties. So for example, calcite. Okay, listen up. If you are just kind of like doing something else, playing a game and listening to this in the background, please turn it off and listen, because this is very important. Okay. You can go back later, I guess, but I mean, I don't recommend it, but I mean, but listen now. Calcite. One special property of the very, very, very important mineral calcite. Okay. By the way, the chemical formula calcite is CaCO3. Calcium carbonate. Okay. You should know that. You should write that down and just memorize it. Write it on your forehead. Calcite, it reacts vigorously with acid. Okay, acid in any form is very good at breaking down calcite. So you can see that we put a little drop of acid here on a sample of calcite, and it's bubbling and reacting. Okay, so it fizzes with acid. It breaks down with acid. Okay, so anything acidic will break it down. Well, guess what? A lot of water is slightly acidic. Okay, because CO2 will dissolve into the water. It will form carbonic acid, and it will break down your calcite. Now, another very important thing. There is a mineral called magnetite. Very, very important. Again, if you're not listening, listen now. Magnetite is a very common mineral. It's found in very many rocks, okay? And it is magnetic. Okay? It's magnetic. So you can see these are nails just sticking to samples of calcite, okay, or samples of magnetite, pardon me. Okay, it is magnetic. So that's very important. All right, again, you'll see why it's important. It has huge implications for Earth and the study of historical geology. It's crazy in a way. This wee little mineral, this one little mineral, magnetite, we have learned so much about the history of Earth from this one mineral, magnetite. It tells us so much. I mean, like if we didn't have magnetite, it would almost be like we wouldn't know really very much about what has happened on Earth. And I'm going to show you why. And it's going to be a process, kind of unpacking all this and unfolding it for you. But you're going to see how important this mineral is as we go forward in the class. Some other just kind of wacky random properties. Some minerals have a distinct smell. Sulfur smells like rotten eggs, for example. There's just almost unlimited number of weird, wacky properties that minerals have. I really wish that, I had everybody here and COVID wasn't around and we could look at some of these things, because I have a really cool collection of just weird, random property minerals. But you know how it is. So maybe someday in the future. Right, halite tastes like salt because it is salt. Okay, so there's just some useful properties. This is another thing I wanted to hit on. There are things in minerals called cleavage planes. You don't need to understand it really, really well, but I do want you to be aware that these things exist. Okay, cleavage planes. Some minerals break along certain planes very easily. So for example, mica, which is a very common mineral, breaks into flat sheets like that. If you were to hit halite with a hammer, see how it breaks into these perfect cubes? If you hit calcite with a hammer, it breaks into these rhombohedral kind of shapes. Okay, that's all from cleavage planes. So some minerals just break along certain planes more easily, and it has to do with that repeating atomic crystalline structure, highly ordered structure. Now compare that to something like concrete. If you hit concrete with a hammer, it's just going to break and crumble randomly like a cookie. There's not going to be any pattern to the breakage. See how there's a pattern to the breakage here? That's cleavage. That's important to know because that's going to control how susceptible a certain mineral is to weathering and erosion. Okay, so I want you to be aware that such things exist, right? So like, for example, mica, this all arises from the atomic structure. So for example, mica, these bonds break very easily, and so that's why you get these sheets that form. Okay, so that is basically like a little bit just about minerals in general. And I wanted to just talk more in depth now about some very common minerals on Earth. I throw some up here right now, which are feldspar. Okay, very common. That is the most common mineral on Earth's surface, is feldspar. Quartz is also very common on Earth's crust. And one that's very common in the mantle, olivine. Okay, remember I said the mantle is greens because of olivine. Okay. So remember that Earth's crust is mostly oxygen and silicon. Mostly oxygen, silicon. So if you go and you pick up a rock outside, probably it's 50% oxygen. It's just 50% oxygen. Okay. So a lot of it is also probably silicon. Depends upon whether you have calcite, carbonate or not, or if you have a silicate rock. But the silicon and oxygen in Earth's crust combine to give us something called a silicate molecule. Okay, so silicon and oxygen together make up 75% of the Earth's crust, and they are going to combine together to give us some what are called silicate minerals. So quartz is a very common mineral on Earth's crust, and the reason quartz is so abundant is because it's made up of the two most abundant elements, SiO2. By the way, you should know the chemical formula for quartz. Okay, so you should be, I should be able to ask you on the test, and I might ask you on the test, what is the chemical formula for quartz? It's SiO2. Okay, one silicon atom to two oxygen atoms. Now, very important, again, turn off the video game if you're doing something else, or turn off the podcast if you're doing something else here, and listen up. Very, very important you know this. So the silicates are the most important class of minerals in Earth's crust, and the most important class of minerals when studying historical geology. So you should know this class of minerals called the silicates. The silicates. The silicates make up a great deal of the crustal rocks and the mantle rocks. In fact, the silicates make up a great deal of the Earth in general. The silicates are minerals. Silicates are minerals that are composed of a molecule called the silicate molecule. This is the silicate molecule that I'm circling over and over and over again. The silicate molecule is like the basic building blocks of rocks. Okay? It is like the most basic building block of the Earth, the silicate molecule. So the silicate molecule is composed of one silicon atom, which has a +4 charge in the middle, surrounded by 4 oxygen atoms that are kind of in what's called a tetrahedral shape. So this is a shape, it looks a little bit like a pyramid, but it's not really a pyramid. It's a tetrahedron, and it has a net charge. You'll notice of we got a +4 here, then we have 4 plus -2, so it gives a net charge of -4. So it is an anion, and it is going to be the building block. So it's going to combine with other cations, other atoms to form minerals. Okay, it's a very important molecule though, so you must know it. Okay, I'm guarantee you I'm going to have questions on the test, the final and the midterm, about the silicate molecules. So you must know this, memorize this, write this on your forehead. You should be able to draw a silicate molecule in your sleep upside down with your eyes closed, because it's important. Okay, so most of the rocks that you see around you are made of silicate molecules. Okay, so if you pick up a piece of granite or a piece of basalt, probably like 50% of that rock or more is just silicate molecules that are linked together in different ways. Now, the most common rock forming minerals are silicate minerals, And these are them. So you got to know these guys. You got to know these minerals, and you have to know a couple of their mineral formulas. Okay, so I got them here. Quartz, feldspar. There's a few different types of feldspars, which we'll be talking about later. Mica, amphibole, pyroxene, and olivine. All right, now these are in a very special order. Okay, the order reflects. Okay, get ready for this. This is kind of in depth and a little difficult to understand. The order here is very important. It refers to the degree of silicate molecule interconnectedness. Silicate molecule interconnectedness. So it is how interconnected, kind of how networked the silicate molecules are. So silicate molecules in quartz are all highly interconnected. They are sharing all of their corners. So here's a silicate molecule, and in quartz it's going to be sharing, they're going to be sharing all of their, they're going to be interconnected this way. So they're going to be sharing all of their silicate molecules together like this. You're going to get these kind of star patterns forming, things like this. So anyway, I don't want to draw out the whole, in fact, I made a mistake right there. It shouldn't be like that. But anyway, ooh, there we go. Okay, I have to stop drawing things. Silicate's very interconnected. You could think of the silicate molecules in a quartz as being like very social. They're like salesmen. You know, they're very interconnected. They like to network. They like to be connected to everybody. Okay, so that's how the silicate molecules in quartz are interconnected. So feldspar is a little bit less interconnected, but still very highly interconnected. And you'll notice that these are both very hard minerals, right? Very hard minerals. Why are they hard? It's because the silicate molecules are interconnected. That's why. Okay. And why are they resistant to erosion? Why are they such tough minerals? It's because the silicate molecules are interconnected. Okay, that's why. When the silicate molecules aren't like bonded together, it makes it a weaker mineral. Mica, okay, has a little bit less interconnectedness. Amphibole has even less. Pyroxene has even less. You get all the way down to olivine, in which the silicate molecules are not interconnected at all. They are all separated, and that makes this mineral easier to weather and break apart. Okay. So the 5 basic structures of the silicates. So silicates have different degrees of interconnectedness. Okay. Olivine. You should know the formula of olivine. It's Fe, which is iron, or magnesium, 2 SiO4. So basically, for every silicate molecule, SiO4 is a silicate molecule, you have 2 of these atoms, whether it's iron, whether it could be both iron, it could be whatever proportion of iron and magnesium. Okay. So olivine is a green mineral, very common in the mantle, and it's also common in crustal rocks as well, especially oceanic type crustal rocks. These are totally isolated tetrahedra. So we call these the isolated tetrahedra. Okay. So you can see that the tetrahedra, the silicate tetrahedra, the silicate molecules do not touch. Okay, they are not connected. These are like the lonely computer gamer loners who don't talk to anyone. They just live in their parents' basement, and that's what olivine is like. Okay, so it's no social connection between the silicate molecules. Now, the next one, right, is pyroxene. So pyroxenes, of course, pyroxene, by the way, is a whole family of minerals, right? But pyroxenes, the silicate molecules are connected in a chain. Okay, so you can see that every silicate molecule has 2 members that it's sharing with. Okay, so he shares with 2 others. This guy shares with 2 others. This guy shares with 2 others, right? And so they share, kind of holding hands in a long chain. Okay, so that's the pyroxene molecule. Okay, so these are people that don't have like big social structures and big networks of friends, but they have 2 people that they're close to. Okay, that's the kind of way that you can think of pyroxenes. Now, the next one, getting more interconnected, are the double chains or the amphiboles. Okay, amphiboles are double chain silicates. So you can see that it's like it's actually just two chains that are connected themselves, right? So you can see that every atom is going to share with one, two, every silicate molecule, some will share with just two, but some you can see share with three. Okay, so this guy shares with three. All right, so you'll see that every other silicate molecule shares with three, every other silicate molecule shares with two. Now, the next one are the muscovite type minerals. These are the sheet minerals. So this is where you form these kind of things. They look like stars of David, these six-sided stars. So it's all these interconnected, and this goes on for infinity. I'm just showing you a piece of this, but these form these big, long, expansive sheets of silicates. So you can see every silicate molecule here shares with three. Okay, so every silicate molecule has three partners. The framework silicates, which are the quartz and feldspars, they are the most. Of the four oxygens, the 4 points, every single one is connected. So you get these huge networks. So these are like the salesmen, highly extroverted types that are networked, and everybody's interconnected in everything here. Okay, so that's the most interconnected. And these things, these different silicate structures, have huge implications for the physical properties of both the crystal, the mineral, and the melt also. And we're going to see that a little bit later as we go on through the course. This has big implications for what the melt, the lava made of this rock is like too. So just to kind of give you some ideas about why all this interconnected stuff is important, has big implications for how tough and resilient and the mineral is. So think about, again, the lonely gamer in his hiding in his parents' basement, right? The isolated tetrahedra of the olivine atoms, right? The olivine tetrahedra. Who's more resilient? Just asking you, who's more resilient to like problems and challenges in their life? The lonely gamer or the person who's very interconnected in their life? And the answer is it's the person who's very interconnected, right? So the framework minerals are very tough and very resistant to erosion. So when you go to a beach, right? This is a beach at Lake Michigan, close to where I did my PhD. You can see that the beach is usually made out of, and the same here, if you go to Corpus Christi beaches, it's the same thing. You go to the beaches, what do you see? You see a lot of white, brownish sand, okay? That is all feldspar and quartz. It's all feldspar and quartz. What happened to the other stuff? It got eroded away. All that's left is the feldspar and quartz. And that's why when you go to the beach, you just see feldspar, quartz, sand, because the other stuff that's weaker got eroded and weathered away already. There are such things as olivine beaches. These are green sand beaches in Hawaii. Okay, they're very rare. I mean, you look at this and you're like, whoa, that's weird. And the reason it looks weird to you is because it's very, very rare to ever see a green sand beach, because olivine usually gets eroded and destroyed very easily. Because why? It's because the silicate molecules are not interconnected. Okay, they're weak. It's a weak mineral. It breaks down easily. It as soon as it gets some weathering, pressure, it breaks down. Okay, so there you go. That's what a typical beach looks like. What is it made of? It's made of quartz sand, right? Because those grains have undergone a lot of weathering and a lot of transport. They've been faced with a lot of problems in their lives, and they have made it through. They've been resilient and survived because they have all those connections with the other silicate molecules. It makes it very hard to break them down. Okay, very tough. So just a little summary of the silicates. Here's the silicate tetrahedra, right? It is kind of this pyramid type shape. Boom, that kind of looks like a triangular kind of shape, has these 4 triangular faces. Tetra means 4, so it's 4 faces. He's got 4 triangle faces. The silicate minerals are the most important group of minerals in earth sciences. They all contain the silicate molecule. They're all made of the silicate molecule. That degree of interconnectedness of the SiO4 silicate molecules in silicate minerals is very important. It determines many physical properties such as hardness, erodibility, and also the viscosity of the melt when these minerals do melt. Okay, so you're going to see that an olivine-rich melt is going to be much less viscous than a quartz-rich melt. Okay, which has a lot of implications too. For it's going to determine how fast that melt moves, how explosive it is, all these different things. So it's all connected to this. So besides quartz and feldspar, mica, olivine, amphibole, and pyroxene, those 6 you want to know. Okay, those will probably be on the test. I'm going to ask you about this. Just some other minerals you should know about are things like calcite is very, very important. Calcite is not a silicate. Okay, calcite is Ca, calcium, CO3, carbonate. This is a carbonate mineral. Another thing that's important are clay minerals. Clay minerals are silicates. Okay, they're actually related to the micas. They're similar to micas, but these are kind of tougher. They're very resistant to breaking down, and but they do have that kind of sheet-like cleavage that makes these sheet-like crystals. And they are also, by the way, sheet silicates, just like the micas are. That's the degree of interconnectedness. Hematite is not a silicate. It is an oxide. It is iron oxide. It's also a very important mineral. It's either Fe2, it's Fe2O3 is the formula for it. Okay, so you should know some of these formulas. Okay, definitely calcite you should know. Hematite you should know. You should know quartz. You should know feldspar. You should know olivine. Okay. All right, so calcite here. Calcite is very important because marine organisms use calcite to make their shells. Okay, whether they're macroscopic or they're microscopic like plankton, they use their shells. Or they use calcite to make their shells. When these organisms die and their bodies sink to the seafloor, they form a very common rock called limestone. So most of the limestone that you encounter, believe it or not, is totally made up of the bodies of marine organisms. Whether, again, those marine organisms are macroscopic, like big gastropod shells, or if they are microscopic, like plankton shells. Okay. This is what a carbonate molecule looks like. You'll notice it is different than a silicate molecule, right? It has a carbon atom surrounded by 3 oxygen atoms. These are much weaker kinds of bonds than the silicate molecules. Okay, these are much weaker, more erosive, more erodible, less softer minerals. Okay. Another common mineral you should know is iron oxide. So iron oxide, aka hematite, is a red mineral. So a lot of times when you see very red soils, these are rich in iron oxide. So iron oxide is kind of the last thing to break down when some minerals get eroded and get weathered. Okay, they're like the last thing to break down. And so if a soil is highly leached, if some sediment is highly leached and it's been exposed to a lot of weathering, you'll see it's very red because all that's left is the iron oxide. Okay. Another very common type of mineral are clay minerals. Okay, there are a lot of different types of clay minerals, from kaolinite to bentonite to montmorillonite, and there's so many more. You don't need to know all those different types. This is just an example of the chemical formula of one common kind of clay mineral called kaolinite. If you've ever had a milkshake at McDonald's or a similar type of place, you've probably ingested a lot of kaolinite because they like to put this kind of stuff as filler and thickener in their milkshakes. Isn't that a nice thought? So microscopic image of the clay, you'll notice it has this sheet-like appearance, okay, kind of like the mica, that it has this layered structure. So that's kind of why when clay minerals get together and form rocks, they form a rock called shale. And you'll notice, do you guys see the relationship between this image and this image? So again, it has this very sheet-like, flaky sort of atomic structure that ends up forming these very sheet-like clay, flaky sort of rocks called shale. Okay, many different kinds of clay, but they're all similar in that they have that flat platey structure. Okay. So clay minerals, by the way, are produced by, I want to talk a little bit about how clay minerals are produced. So clay minerals are produced by the breakdown of feldspar. Feldspar, remember, is the most common mineral in the crust, right? It's made of sodium or potassium aluminum Si3O8. When it weathers, it forms clay minerals like kaolinite plus quartz plus potassium ions. Okay. So there's a good reaction showing you where those clay minerals come from. So you have to just realize there's going to be lots and lots and lots and lots of clay on the earth because there's lots of feldspar. And when the feldspar reacts with water, right? So you see the orthoclase feldspar reacting with water, and if the, like I said, most water is slightly acidic, so you get this little bit of acidity in the water. It breaks it down into kaolinite plus quartz. Okay, so that's how that all works. I just want to kind of end here with some, just kind of want you to be aware about how we use minerals, because we as earth scientists and geologists, we use a lot of minerals, right? So I mean, everybody uses a lot of minerals, but earth scientists and geologists are the ones that discover them. But they have a lot of different properties. So for example, fluorite, we use fluorite to make high quality scientific lenses and glasses for telescopes. Halite, which is rock salt, we use that both to ingest in our food, also to clear roads, icy roads, right? We can use rock salt to melt the ice. Gypsum, have you ever heard of gypsum board, right? So gypsum is actually a very common building supply. It's plaster of Paris. If you've ever heard of plaster of Paris, we use it to make like the drywall, right, in our houses and buildings, things like that. Galena, which is a lead sulfide mineral, right? We use that as a source of lead for batteries. Hematite we use to make any kind of iron or steel, right? It's a source of iron. Uraninite, which is UO2, right? Uranium ore. We use that for energy, right? Because we use 19% of our electrical energy in the United States comes from uranium, right? From nuclear power. Quartz is used to make our glass. Okay, all your glass and glassware and windows in your house comes from quartz. Graphite is used, of course, for pencil lead and for also lubricant as well. You might have seen before graphite being used to like loosen locks and things like that, lubricate locks in your house. And of course, diamond is, besides being a gemstone, is also useful for diamond saws and things to cut through solid rock. Okay, so minerals are naturally occurring. They're solid, shaped by geologic processes. They must have a crystalline structure and a definable chemical composition. Okay, they have patterns of repeating atomic arrangements. So just ways that they can be used, what they tell us. Okay, these are all things that are probably going to be on the test. So you got to know. It's just a summary of key points I hit on today. So here's some exam questions that will, of course, will be asked in multiple choice format. But what are minerals? You should know those 5 characteristics of it. How do minerals form? Right? You should remember the 5 different ways minerals can form. I talked about that. Precipitation, crystallization from a magma, mineralization, freezing of a gas, and one that is eluding my mind right now. I can't remember. And then what do they tell us about Earth? Okay, I mentioned that in the kind of like first beginning slide. And how are they useful to us? You should also know about the silicate interconnectedness and atomic structure of the silicates. And you should definitely know a lot about the silicate tetrahedron. Okay, you should be able to draw out a silicate tetrahedron easily. Okay, and you should be able to say something about how interconnected, you should be able to say something to me about what kind of physical properties of minerals are affected by silicate interconnectedness. Okay, so with that, I will leave you, and I hope you have a good week, and I will talk to you next time. I think the subject of the next lecture is rocks, if I remember correctly. Okay, so don't take my word on it, but I think it's about igneous rocks. Okay, so I will leave you here, and have a good week.